Let's pick up with graphs of logarithmic functions. Two things to recall here. Our definition of logarithmic functions is that they are inverses of exponential functions. We studied exponential functions and their graphs and saw they look something like this red function here. This f of x is e to the x is graphed here in red. One other thing to recall is what it meant about the graphs of inverse functions. What did we know about them? And what we learned was that they are reflections over the line y equals x. So in this case, that line y equals x, always the line y equals x looks like this, right? And so if you fold on that green line, those two graphs, the red one and the blue one, will indeed be on top of one another. So g of x is the natural log of x, is the inverse of e to the x. Same base, remember natural log of x is base e. Okay, so that's a little bit about graphs of logs. Let's talk about the properties of those graphs and the function itself. If you recall, the exponential function had domain of all real numbers. Let's just do a little refresh here. Exponential function, the domain was all real numbers. The range was 0 to infinity, not including the 0, right? So when we go to talk about the domain and range of a logarithmic function, the range will be the same as the domain of the exponential because you're switching the two, right? And the domain will be 0 to infinity, which was the range of the exponential. It's just flipping these two. Okay? This function is also 1-to-1, so it has an inverse, which is kind of how we've defined it. Now, if you recall with the exponential functions, the x-axis was a horizontal asymptote. Now, the y-axis is a vertical asymptote with the logarithmic function. That just comes from switching your x's and y's. Look at this graph here, this blue one. As we go down, 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 it gets closer and closer to that the y-axis, and that's a vertical line. There is no y-intercept of this because it never touches that vertical line, but the x-intercept here, if you recall exponential, the y-intercept was 0, 1. In this case, those are switched to give you an x-intercept of 1, 0. And this function will be increasing for a greater than 1. I'm not sure why I didn't include and decreasing for a between 0 and 1. Okay, same thing but that we had before where we had logarithmic functions, or we had transformations on the exponentials. We can do the same for the logs. Let's talk about this. If you were to plug a number in for x, the first thing you would do is subtract the 4. That is a right shift. It is impacting the x. It is subtracting from the x. So you're going to take the whole graph and shift it 4 spaces to the right. This -2 in front is a stretch by 2 and a reflection over the x-axis. Okay. Let's talk about the domain of a logarithmic function. Oh, one thing that's important there is that vertical asymptote will shift with this right shift. So this guy right here shifts the vertical asymptote to y equals 4 also. Okay, if you pick up the whole thing and shift it over, sorry, not y equals 4, it's a vertical line, x equals 4. Pick up that whole thing and shift it over to the right 4 spaces. The vertical asymptote shifts with it, and that so that vertical asymptote will move over to the right 4 spaces, which shifts it to x equals 4. All right, domain of a log, very, very important. Thus far, pretty much what we've seen, polynomials, the domain is all real numbers. Rational functions, you can't have 0 in the denominator, right? Square roots, you can't have a negative inside those. Exponential functions, domain was all real numbers. Here, we have to make a restriction on the domain of logarithmic functions, right? That was addressed here. But this is only applying to this type of function. And so when you start making shifts, these transformations, things start to change. The important thing is that whatever is inside the log, in this case, in this box, it's written as g of x, it has to be greater than 0. So x minus 3 has to be greater than 0. You cannot have a negative inside a log. So in this case, x has to be greater than 3. So in interval notation, that would be 3 to infinity. Let's think about y. Remember, you are asking yourself 5 to what power is equal to x minus 3, right? 5 to the f of x, or if this were y, that would be a y here. Okay? Well, 5 to any power can't be negative. No matter what the y is, you cannot get a negative out of that. So x minus 3 has to be positive. It's the only way for this to work. In this case, we want x minus 4 squared to be greater than 0. Well, the good news about that is that x minus 4 squared is always greater than 0, except when it's equal to 0, right? No matter what I plug in for x here, except for 4, that can't be 0. If you want to think about what x minus 4 squared looks like, it's the standard parabola shifted to the right 4 spaces. And it opens up like this, right? Rough sketch. Well, that is always greater than 0, except at that one point at the vertex. So x equals 4 doesn't work because there's no equal sign here. The domain in this case is negative infinity to 4, union 4 to infinity. Okay? So an important thing, the base can't be negative. The what's inside the log cannot be negative. All right, that's it for our introduction to logarithmic functions. Be sure to practice these a lot because we're going to continue to use them throughout this chapter, and we want to make sure that we have a good firm foundation in understanding logs.